Are you guys
You can
able
see
to
your
see?
screen.
Yep,
Yep.
it's available.
So this chapter is sort of building on the previous one, which was decision trees, and in general, a class of machine learning models that sort of depend on the collective rather than the individual models. And this is kind of inspired from sort of a notion called the wisdom of the crowd. So when I was looking this up on Wikipedia, I actually came across a um, uh, pretty interesting example. So let me see if I can share. One second. I do apologize. Okay. So are you guys able to see the Wikipedia article on the left of
Yeah,
the screen?
yes.
Perfect. Yeah, so this is a very fascinating article. So I originally started looking at this, which was the wisdom of the crowd, which basically said, kind of brought a few things into context. So whenever we look for some answer to a question that we are searching for, say in Quora or Stack Exchange and so forth, we typically try to see how many people have given the same answer or similar answers, and then sort of derive our conclusions, sort of reconciling ourselves, saying that, yeah, so many people seem to agree on this, so that this must be the right thing. And this is the inspiration for most of the ensemble learning models. So this is where the inspiration for building ensembles came from. And on a related note, there's this secondary article that I stumbled upon, which is the jury theorem, which says that it kind of tells you how to pick the ensemble in a sense. So if you had to pick a jury, if you had to pick a group of people to come to a decision on a particular case, this theorem is a very simplistic way of saying how would you choose the jury. So if the probability that each juror votes independently and is going to be giving you the correct decision is greater than half, then you will succeed in getting the right decision by adding more jurors into the mix. Whereas if the individual probability is less than half, you're probably better off adding lesser jurors into the mix. And this was kind of a very fascinating analogy to kind of this chapter. So sort of going back to what this chapter is about. So the wisdom of the crowd basically says that instead of relying on a single observation or a single prediction, aggregate as many predictions as you can, and that's what ensembles are. So a group of predictors is an ensemble, and this method is called ensemble learning. So here we can see that you can train a different set of decision tree classifiers, each on a random subset of the training data. And then when you aggregate these results, you will find that they do a lot better. And this turns out that this is actually a random forest. So in this case, it's actually good to see the forest and miss the trees. Um, so these are sort of a broad class of models called voting classifiers. And there are two different types of voting. The very first type of voting is called hard voting, wherein what you do is, given a single set of training data, you are going to train individual models like, say, logistic regression, an SVM model, say a random forest and so forth. And each of these models is going to give you a different set of predictions on the same data. And then what you do is you just combine them by taking the majority. So for any given instance, so let's say that I have to predict whether, say, an image is a cat or a dog, and let's say that 3 of the 4 models say it's a cat, then I'm just going to take that as a majority prediction and go with it. And because I'm sort of just taking the prediction directly and taking the majority, this is such a classifier is called a hard voting classifier. So as you can see in this particular diagram, you have that 3 of the 4 models have predicted class 1. There's only one that's predicted class 2. And you are obviously going to go in a hard voting scenario with the class 1 because that's the most popular vote. So interestingly, this brings out a very interesting observation. Even though these individual models might be weak on the data set, so if you were just to use them in isolation, you'd probably not end up with a very strong model. When you combine them, it turns out that they are actually pretty good. And the more number of weak learners you put together, and provided they're sufficiently diverse in the sense that one model is making up for the mistakes of another and so forth, you can end up with a pretty strong learner. And that's why ensembles are successful. So,
A question?
Sorry?
I have a question or a comment.
Sure.
It's strange that he used 4 as an example, because what I saw was in hard voting, it's majority. And what happens if 2 predict correct and 2 predict false for the class?
I would think you would choose a random um,
So it would seem to suggest that if you use hard, it's better to use
an odd number.
odd number for your classifiers, isn't it?
Yeah, that's always true. So typically when you train your ensemble algorithms, you would choose to go with odd number of ensembles.
Yeah, so that's why I'm surprised he chose even, because when you look at the code or the comment in sklearn, a hard says majority. So majority can't be achieved if you have an even in cases where it's split.
I think the best way to implement that would be to just do a random flip of a coin to determine whether you're going to take the one class or the other, and then it would be completely fair.
But
Yeah,
when you're
I'm saying if you use the hard as he does in the voting, and if you use 4, I don't know by what means. It could be that it just picks a random class, but that would argue for if you choose sklearn and using hard, then it's better to go with odd number just so that you can ensure majority either way.
So
Right, but you might not have a choice, right? I mean, you might have an even number of samples.
No,
then
no,
what do you
it
do?
doesn't depend on the samples, right? It depends on the
so
number of
talking about number of
classifiers you
classifiers.
use.
And that you can still get
Class.
even
Right.
distribution, right?
Oh, I see. You're saying you should choose an odd number of classifiers to
Yeah,
do that.
right. Exactly, because then you're ensured that you
Not
will...
really, right, Srinivas? If you have 3 classes, you can have still 2 giving you 2, 2, and the third one will give you 1. In a binary case, yes.
Yeah, binary is what I was thinking right now.
That case, yes.
So the other comment that probably might help out is that there is a mention here that each of the weak learners are sufficiently diverse. So the hope is that you sort of split the tie in some sense, because the learners are each making different types of mistakes. But you're right, in general, as a practice, it might be it's probably good sense to ensemble an odd number of classifiers, I guess.
Yeah, it doesn't matter in soft, but in hard, it seems to, and I was kind of surprised by that, which is why I made the comment. Okay.
Correct. Interesting points. So the reason that, so this is something that I was actually curious to get the group's thoughts on. So here the author sort of goes into the law of large numbers, which says that if you, sorry?
Sorry. I mean, like somebody actually posted a link to Stack Overflow, which would actually explain what would happen in the scenario of having even classifiers. It's pretty good article.
Epsilon,
that
where they did
available?
mention categorically that in the cases of a tie, the voting classifier will select the class based on the ascending order, if they are sorted in ascending order. So I think let me share it in the Epsilon if you look at it here as well. So if there is a tie, you need to arrange the prediction in ascending order or descending order,
I see.
sort of order,
In
and you
case of
select
a tie.
classifier which one appear first, and it is there in SQL.
So it's saying that in case of a tie, the voting classifier will select the class based on the ascending sort order in the following scenario. So ascending sort order of the label.
Yeah.
Okay, that's interesting. So that's a pretty random way to break the tie, but looks like that's what scikit-learn is using.
Yeah.
Cool. So one of the things that I sort of wanted to get from the group is that the author mentions the law of large numbers, which says that if you have a slightly biased coin, it's going to give you heads 51% of the time, and you do this experiment sufficient number of times, you do generally end up with like 51% of the total number of experiments as heads. But then he goes on to mention that if you do the math, you will find that the probability of obtaining a majority of heads after 1,000 tosses is 75%. Can somebody sort of talk about why this is the case and sort of how this happens?
It's just that the probability to the power of this thing. So he's assuming that it's a binary class classification. I mean, it's a binary class, right? 51 point. It's just a probability that if you expand, it would boil down to 75%. Binomial probability.
It just means not the binary flip. It means the majority is heads, not necessarily.
Right. So you'd have to sum the binary. See the binary. So the binary. The binomial distribution is defined for a problem where you have a probability. You're given a probability of success. You're given the number of successes, and you're given the number of total trials. Right. So. So if you have those three numbers, you can calculate the probability that you will have that number of successes out of that number of total trials. So in this case, we would want, let's suppose we have 1,000 trials, then we want the probability that 500 or more of those trials are successful in the sense that that you'll get a heads, let's say, right? So the probability is going to be let's say n is the number of trials and m is the number of successes. Then the probability will be the binomial probability will be n factorial over n minus m quantity factorial times m factorial. That's just n choose m in combinations, right? And then that number gets multiplied by the probability of success to the power of the number of successes, which is m, times the probability of failure, which is 1 minus p, to the power of the number of n minus m. That's the number of failures. Yeah. So if you look up the binomial probability, you'll see, and all you have to do is sum it. If you want more than half successes, you just have to sum it from 0 to 0 successes up to 501 successes. And then that's that number he's talking about, which gives you that number of 75%.
Nice.
So, I mean, it's hard to explain without a whiteboard, and I'm sorry about the confusion.
So I just shared a link, clicked a link that one of our participants shared on the chat. So is this sort of the setup that you were talking about, Joseph?
Yeah, Q, let's see, Q is the problem, P is the probability of success. Oh, let's see, and 1 minus P is the probability of failure. So for each, this isn't exactly, let's see. No, let's find another.
Okay.
If you look up binomial distribution on Wikipedia, you'll see it.
Like it would be this example if the probability is 51 instead of 50, because in this one is using 50.
Yeah, so you end up with 25%, and which is like 1 minus 75, right? It's the same problem.
Yeah. So here's the n choose k. You see, that's the factor that goes in front, and then the p to the k is that probability, which in this case will be 51% to the k, which is the number of heads, times 49% times, that is 0.49 to the power of the number of tails. But the key thing is you have to add this up from 0 to 500. Actually 0 to 501, because you want the probability that you'll have more than half successes.
So this basically.
Yeah. Instead of summing it, and k would be half of n, the number of trials.
Right.
Yeah.
Okay. Yeah, so I was just curious because I was trying to reconcile between sort of the numbers he posted here, and then the graph basically seems to suggest that you end up with 51%, and then I was wondering where he got the 75% from, but this makes it clear. Anybody else have any questions or comments here before we sort of continue?
Yeah, so anybody that wants to get that number 75, just, you can easily set that up as a problem. You can easily set up a little Python code to compute it. And that's where I'm expecting you're going to get the 0.75.
Yeah, it's interesting that he doesn't mention anything related to the central limit theorem in statistics, because that seemed to be a little bit more applicable, but I'm not an expert in this area, because there it's the mean of the sample means that you're kind of slightly talking about, and the variance of that is much smaller than the variance of the original distribution, and that's the sort of thing I thought was playing into this.
Yes, that's exactly right. I mean, when you average together a bunch of things and each one of them has an error, then the error in your estimate is going to be smaller by the square root of the number of things you're adding together. So if you add together like 25 different predictors, each one of them is independent, gives you an independent estimate of something, then adding together those predictors should give you, or averaging together those predictors will give you, an improvement in the error of 1 over the square root of 25, or 1 over 5. It's going to cut down the error by a factor of 5. So that's the way that works. If you add together a bunch of independent predictors, then it cuts down the error by square root of n, by a factor of 1 over square root of n.
Is that 1 over square root of n a specific condition, or I'm just wondering why it's not 1 over n?
Because it cuts down the variance by 1 over n, but it cuts down the
okay.
error by, yeah.
Okay.
Cool. So that actually brings a lot of this particular section into context. So I was kind of struggling with why it was 75%, but now that's clear. So the author's comment is that if you ensemble 1,000 classifiers and individually each classifier is right about 51% of the time, which is slightly better than a random guess for a binary classification problem, you'll see that the majority voted class would have that you could possibly get 75% accuracy with the ensemble. However, this is only true if each classifier is truly independent, which is, and they make uncorrelated errors, which is not always the case, because when you give the training data, you would find that more often than not, individual classifiers tend to make somewhat similar errors. They're slightly correlated and they're not completely independent. And the number that you might see from the ensemble from hard voting is probably lesser than 75%. However, that raises a very interesting point, which is why I kind of highlighted it here. The ensemble methods, they work best when your predictors are as independent from one another as possible. Basically, there are two strategies to get them to be as diverse as possible. The first one is to train them on very different algorithms, meaning, SVM, logistic regression, and so forth. The second strategy is actually to sort of help them train on different samples of the training data, which is something that we will get to as we continue this discussion. But this is something to keep in mind if some of you folks are working on, say, a Kaggle challenge or something, and you want to improve your result. It's probably good to ensemble a different set of predictors as opposed to, say, taking two support vector machines and then trying to ensemble them.
So here when we say sampling different parts of training set, is it the same?
I'm sorry, I couldn't quite catch that. Can you repeat that, please?
Sorry, I think you had. What I'm saying is, like, when we say that the chances of predictors being different are improved when we
your voice is breaking up. I'm sorry if I'm the only one who's experiencing that. Is anyone else able to get it?
The same as well. Can you please type in? We can move in the meantime. I think he'll type.
Okay.
I have a question, if I may.
Go ahead.
Yeah. So is there any scenario where you would choose hard voting classifier over soft? Because it seems like soft is always better than hard.
The only scenario that I can think of is when your model cannot predict probabilities. Like there might be some models that only give you predictions as opposed to probabilities. And for those scenarios, I think there's a paragraph in this chapter where the author mentions that if there is a way for your model to get probabilities, then scikit-learn by default helps you do soft voting or something like that. So the only guess is that you'd probably use hard voting when you can absolutely not get any probabilities on your prediction from a model.
Okay.
Any other questions before we sort of move along?
Okay, are you able to hear me better now?
A lot better, thanks.
Yeah, I connected to my phone. Okay, so what I was saying was, if the each of the predictors, if they're trained on different parts of the training set, to help them be more uncorrelated. So would that be the same as cross-validation, where we are doing different parts of the training set, right?
You're talking about KFold cross-validation.
Yeah, KFold.
Possibly, but I think what the author is referring to here is like you want to ensemble models that make different types of errors. So let's just say that even if you do cross-validate, your training data still has the same distribution. So chances are the model that's learning from it is going to make similar errors. And if you take two models that are sort of trained on different folds, then ensemble them, chances are you might not see such a big bump. Maybe I'm wrong, somebody else can correct me here. But at least in my experience, I've seen that when you take two completely different models and on top of that do this whole K-fold idea, you typically end up with better results when you ensemble them.
Yeah, but what Anand said is, I think, correct. I mean, he talks about pasting, which is, he talks about bootstrap. It's called bootstrapping or bootstrap aggregation or bagging. That's one way of selecting a sample, of choosing from your sample. And another way is called pasting. And the difference is that for bagging, you choose randomly, but with replacement. Mm-hmm. Whereas with pasting, you choose randomly as you build your sample, but without replacement, you see. So so when you make cross-fold validation, when you make a fold, you're doing pasting because each sample is distinct from the others.
Correct. So my comment was basically like, would you hope to get something like the 75% accuracy that is being quoted here? My comment was like, that's probably less likely when your individual models are the same. You might see an improvement, but not to this magnitude. But if you have different models, let's say you had a logistic regression model and say an SVM, chances of ensembling them would yield better results, wouldn't they?
Yeah, you're absolutely right. Agreed. I mean,
yeah. To add a point to that, I mean, if your data set is not really that big enough, pasting sort of leads to the shooting in your own foot, because you end up actually feeding a very minimal amount of data to your algorithm, even though your algorithm is quite powerful. Because of lack of data, it may give you the perfect output.
So, and also to go back to the cross-validation question. So yes, you can look at it from that perspective. So, and he mentioned somewhere the out-of-bag instances. Yeah. So yeah, your logic, how you thought about it, is fine. So like you can look at that portion, the out-of-bag instances, over the many predictions that you do, and you can look at that in a way kind of like similar to the KFold cross-validation. So and again, here we're talking, within the training. So yeah, so the way how you thought about it, it's fine. And I think he does mention that somewhere.
Okay, yeah, because I was essentially thinking of combining both the approaches, basically, because when I'm cross-validating, it looks like I already have these multiple
well, here's the thing. What do you mean combining? But because like if you do this, you don't need to do the cross-validation if you just do it this way.
This is like either or.
Oh, by combining, I meant to actually do an ensemble after I do a cross-validation, whereas previously I wouldn't have done the ensemble. Out of just.
Are you saying train each fold on a different model, something like that?
Yes. So like if you want to do cross-validation and then and then do any of these, that's maybe an overkill. Like, you don't usually see cross-validation done with this. That's why he mentions the out-of-bag, that if you want to really evaluate and assess this on your training, you can actually just do that. For example, here, the default in scikit-learn is 63 or something. So you'll have that 37%. It's in a way you're kind of like doing that like threefold cross-validation, and then at the end you can get what's the aggregate, what's the average on that 37%.
Okay.
Yeah, but like doing them both, I mean, hey, if please, if you do them both and you do get a better result than one, share. But still, again, just you're doing so much compute for, I'm not sure how much percentage you're looking to.
Right. Yeah.
Just to clarify something there, so to try to decorrelate as much as possible, the best solution is trying to use different kinds of models, right? You cannot try to decorrelate your data that much because, I mean, you're trying to find a pattern in it, so there is some correlation.
Correct.
So trying to do KFold, or it's not going to really try to decorrelate your data. Whereas trying different models, your models are trying to look at different things and trying to optimize different things. So that's where the sort of the errors made, like what you mentioned, is different, right?
Right. So I think the comment here is, I mean, that's what I was confused about initially when Anand sort of made that comment. His point is that you can still ensemble things. You probably won't get the same boost in accuracy that you would by having decorrelated models, but you could still train this, the model on or models on different subsets of data and hope to get a bump by ensembling them. I think that's the general theme. Does that clarify?
Yeah.
Okay.
Yeah, I mean, what I meant to say was basically, yes, I do agree that using completely different architectures, different models will give us a better decorrelation. But since it is brought up in the book, the point that even the same kind of architecture trained on different samples, different of the same training set, can still provide some decorrelation, maybe not as much as different models. I was wondering then, because it will be more effort for me to train multiple architectures. Instead, if I were to collect the results from different folds and ensemble them, I might do better than using just one single model.
The way I look at KFold is, I mean, KFold is basically you're looking at your whole data just at different instances of training, right? That is the difference, at least I see, versus when compared to like if you were training different models. Like if you were doing like a 20% split, that 20% is never seen, right? Only the 80% is always trained on. The KFold kind of obfuscates that. And then it looks at that 20% also at some point of time.
Typically, KFold is used to actually calculate the metric. What are the metric? Let's say I want to understand RMSE on the entire data set. KFold is a way of actually figuring out that RMSE. You're trying to actually minimize the variance in your error metrics. That's how I see it. And again, every time you chop off some data before you feed it to the model, you're sort of choking the model performance.
That's okay. Yeah, let's move on, because it's the same as bagging. I think when we come to that section, it's basically the same thing that they're saying.
Yeah, the thing is, ultimately, the gain you expect is from the fact that when you use less data, that means your bias is increasing, and you hope that the variance is reduced, but that's not any guarantee. And what is guaranteed though is your bias will increase when you use less of the data in each of the folds than what you have when you have the whole data set for training. So your bias increase is guaranteed. Your variance reduction is, if it happens, then, and it's more likely in highly parameterized models that your variance will go down. Therefore, you might see some gain. That's the way to think of it.
Essentially, you're better likely to generalize because your variance is going down, and that's
Yes.
sort of the gains.
And actually what is guaranteed is your bias is increasing when you use less of the data than all of the data in your training set.
Yes, but you get to you get some of that back when you average together the folds. So it's true that for each fold the bias will be higher, but now you're averaging 5 folds, results from 5 folds, and that will cut the bias back.
Oh yeah, yeah. But what I was getting at was what Anand was saying, right? Like, can he get as, and it's all relative, and he can try it, and it depends. But what is surety is the fact that if you use uncorrelated models, as Rekil was saying, then you are sure to get an increase in your eventual score by ensembling. If you are using subsets of the data, it is probably less than what you would see with uncorrelated models, for sure, but how much? It's an open question.
Yeah, that's absolutely true.
And lastly, just to add on that, so let's just always also keep in mind, like when we're talking, for example, where we brought up cross-validation. So we're talking about training and generalizing our model. That's like that's one point, and there is the validation part. So they are different. So actually, what we're trying to do here, we're trying to generalize the model. And then, okay, once we have the model, then we would be looking into validating the model, and then you can use whatever way you wanna how you wanna do your validation. You wanna do your validation on your test set, that's fine. You wanna do your validation using the cross validation, that's fine. But again, here there is no need much to do the cross validation there, because if you trained it this way, you already can have the out of bag aggregation there, instead of the cross validation. But let's just remember that there is the generalization, the training, and then at the end there is the validation. How good is our algorithm?
Right, but I wouldn't say that Salim is saying, you are saying that that you have from the out-of-bag estimates a means of estimating the generalization error, right? By evaluating the model on the out-of-bag errors for each tree and then averaging them together, you get an estimate of the generalization error.
That's correct. Yes.
Yes, that's what you're saying. But what I'm saying, what I would like to say is that it is not the best way to estimate generalization error. The cross-validation is still better, gives you still a better estimate of the generalization error. So if you have the compute time, even if you are using the random forest model, it's good to use cross-validation to estimate the generalization error and not just rely on the out-of-bag estimates.
A comparison, for example, on the example that he showed.
Yeah, it came out the same. It came out the same, but it's not generally going to come out the same. So in general, cross-validation gives you a better result.
OOB just is like a positive side effect that you can use. Like example, OOB cannot be used if you have time series, right? OOB would fail in time series. You cannot use out of bag there. It just so happens that 37% of the data is not used, so you can use that for that.
So here we're talking. So here we're primarily talking about classification. So if if you're going to talk about regression and like now time series, that's different. But within classification, yeah, I think what we've been talking about is correct. Yeah, and your point, Joseph, it is correct. Yes. So after that, you want to so here it was the same. I'd be curious on maybe on a different data set, but yeah, sure. You can validate that.
In the interest of time, let's keep continuing. I think this discussion will pop up again when we go to bagging, pasting, and the out of bag stuff. So in the interest of time, let's continue. So where we left off was sort of this example. So as you can see, he's kind of taken that diagram earlier and then converted it to code. And you can see that the individual models are all at about 86, 89. But then when you use a hard voting, I think this is hard voting. Yes, correct. So this is a hard voting classifier and ends up with 90%. So there you go, wisdom of the crowd. So what is soft voting? If all your classifiers have probabilities as opposed to just the predictions. In case of a classification problem, you're coming up with labels. So, but instead, if they can tell you the probability of the classes, then you do something that's a little bit more elegant, where you can average the probabilities and then pick the class that has the highest probability across all the models.
I have a question here. When you're averaging it out, how do you have a class with a higher probability? Let's say I have three classifiers for a binary class classification. The first probability is 50%, maybe second one is 55, third one is 60. If I average out, I'll get one probability. Then what does he mean by pick something which has the highest probability?
So, so regardless of whether it's a binary classification or a n-ary classification, you're still going to have probability values that each individual model is going to give for
Correct.
every single class. Now,
Got
if
it.
I have three models, I'm going to take the averages of the probabilities for each of those classes across all the three models. And then I'm going to pick the class that has the highest probability value after doing that averaging.
Still don't understand. Sorry.
So if you average over, so you get a prediction, you get a probability for each class for each example, right? So over all the examples, you average the probabilities in class A, the probability to be classified as class A, the probability to be classified as class B, and the probability to be classified as class C, right? And so you get three numbers. The overall probability for class A, overall probability for class B, the overall probability for class C, and you just pick the class that got the highest overall probability.
You create one other value, and therefore you now have four values, and you pick the highest of the four. That's the way to think of it.
The fourth value, I'm not quite sure how that works. So let's
the average
take a
of the
concrete
three.
example, right? So let's just say that in this particular diagram, let's say that we have two classes to keep things simple. So class A and class B. So every model in this ensemble right here is going to give you probability values for each of those classes. And then I'm going to average the probabilities for class A across all the models. I'm going to average the probabilities for class B across all the models. And then I'm going to take, so now I have one pair of probabilities, right? And I'm going to pick the one that gives me that is greater of those two. And then you sort of can extend
Highest of
this.
all averages. Does it mean that highest of all averages, right?
There is only one average, right? So after averaging, the class with the highest average value.
Okay, got it.
I mean, one way to think about it is the difference between a hard voting one and a soft one would be, let's say it was the two classes A and B, and three of the classifiers voted for A, and the fourth one voted for B. But so the hard voting would have chosen A. But if the guys who voted A only did it with 10% probability, but the guy who voted for B did it with 99% probability, then the soft voting would have chosen B, because that was the highest, even though three others voted the other one, but they had low probability.
So the advantage of soft voting is really that it encourages highly confident votes as opposed to just taking the majority. And that's the reason why it's somewhat better. So when you do the, sorry,
Thanks.
go ahead.
Yeah, thanks. Let's move, I think.
Okay. And so let's see, any other questions here? So the soft voting is basically averaging across probabilities. Hard voting is taking the majority prediction. That's the key difference here. And now we sort of go into this discussion of bagging and pasting. So we saw how we could use different set of classifiers to get very diverse predictions and then sort of average them. The other approach is to sort of diversify the data in a sense. So the way that that's done is you take the same training algorithm. So in this case, you're going to basically train every model that you have on a different subset of your data. And when you do this with replacement, this is called bagging or bootstrap aggregating. And when you do it without replacement, meaning that once a subset of data has been taken for training by a certain model, it's never ever seen by the other models that are yet to be trained. that is called pasting. So in a sense, bagging and pasting allow your training instances to be sampled multiple times by all the predictors in your ensemble. But only bagging gives you that possible chance that the certain training examples might be seen by more than one model. So in this case, so if we have an overall training set right here at the bottom, then we have 4 models. With bagging, what we're going to do is we're going to first go to this model. It's going to take a subset of the training data. It's going to be trained. But then once we have sort of taken a subset, we say that this subset can be reused for the rest of the models. And so the next one will also take a subset of the data, possibly with some overlap or maybe without some overlap on the previous set, and then be trained and so forth. And eventually we're going to ensemble these. With pasting, what we do is once we suppose, let's say that the first model is going to take all these blue samples, then the next model will not be able to access those blue samples. It will only have to choose from the remaining, and so forth and so forth. So eventually every model sees a different subset of the training data, and then you are going to ensemble them. So I see a couple of comments in the chat. So what is the probability of a sample not being drawn in the Bootstrap sample? So I think there is some text in the next page about this, but essentially I think like every model sees on average about 63% of the data, and the remaining 37% goes into something called the out of bag. And I think that sort of when we get there, we can sort of talk about where those numbers are coming from, because I'm curious as well. So sorry, go ahead.
There's a mathematical derivation. If interested, I can find it out.
Cool.
Could you explain? Okay, sorry, go on.
Yeah, I actually had a question regarding like scenarios in which you'd prefer pasting over bagging, and I just want to throw those out there and see if it makes sense to the rest of you folks.
So here is I had the exact same question, so I looked it up online, and essentially the consensus seems to be that when you have very, very large data sets, pasting is something that you might want to use. So essentially there's 2 scenarios when it'll help you. So when you have very large data and you have very limited compute, then it makes sense to have multiple models trained on subsets of this data and then stack the aggregations, right? So stack the predictions. Yep. Whereas bagging in general is sort of better because it tends to reduce the variance while still giving you the same amount of bias as every individual predictor. So in general, it seems like bagging is preferred. But if you are sort of at a budget when computing power is concerned and your data set is large enough, then potentially you can do pasting, because then you don't lose out on sort of not having each individual model seeing similar subsets of the data.
Okay. And would using pasting also be a way to kind of like decorrelate your model? Like,
I don't think so, because like as we discussed earlier, the data is correlated in a sense, right? And what we're trying to do is trying to find that pattern when we apply machine learning to it. The decorrelation is really in terms of the errors that the models make, but I'm not entirely sure if by doing pasting we can guarantee that every model will make different errors. So let's take a concrete example, right? So let's just take that we have 4 logistic regression models and we have this data set and we're going to do pasting. I'm not entirely sure if we can guarantee that by using pasting, every individual logistic regressor will somehow produce decorrelated estimates. I don't think.
I had a similar question, because mainly with pasting, because we are doing it without replacement, we are already guaranteeing that we are seeing different samples, whereas with bagging we might see the same samples. So wouldn't that
Not seeing the
suggest
same samples is not equivalent to not having correlated data, right? Yep. They're 2 different things. Correlation in the data is what you're trying to look pattern up. So if even though you're not repeating the sample from one to the other, I don't think that's what the correlation is being meant to.
Sorry, yeah. I just wanted to clarify.
Sorry.
The second paragraph on the right-hand side at the top, it says, in other words, both bagging and pasting allow training instances to be sampled several times across multiple predictors, but only bagging allows training instances to be resampled by the same predictor. So it seems like all the training is going through all of the predictors, but only bagging allows the given predictor to resample the same data.
So
right, that's true. And also, if your data does not actually follow IID, IID, identically independent data distributions, then pasting seems to be a better one, is what I actually feel. If there's a lot of correlation among the individual data points, bagging may actually not be the right one.
So if whether or not the same samples are seen again does not affect the correlation, then I'm still trying to understand how bagging and pasting are different in terms of their how the variance is reduced or not.
So in bagging, one of the things that you are doing is, so if you take pasting, you're basically guaranteeing that every subset of data that a predictor sees is different from the others, right? In bagging, you're sort of doing with replacement. So there's a chance that some of the samples that were previously shown to one predictor can be shown to another, right?
I don't
And
think that's
also
necessary.
for the
Like,
same predictor itself, it can probably resample some of those training instances. So in that sense, bagging has a chance of reducing the variance more than pasting, because pasting sort of is encouraging every predictor to sort of overfit on that subset that it sees. Whereas bagging, you're reducing that likelihood because it's seeing sort of with replacement, if that makes
I
sense.
think even in pasting, the subsets would be quite similar.
How so?
It's not different subsets of the data that goes to each predictor. Each subset is done without replacement. Like if I'm taking M samples from my data, I would just take M separate ones. Whereas in bagging, I would randomly pick M out with replacement. So the same training example might come a couple of times.
Correct.
Whereas so it is not necessary that, I mean, it would never be the case that each predictor would get separate subsets. Like if I have 100 in my training set, my sample size, suppose it's 90, then in pasting, the first one would take 90 separate ones, the second one would take 90 separate ones. So obviously most of them would be same in the first predictor and the second predictor's data sets.
I'm not sure if that would be pasting, right?
It says clearly in that paragraph, right? Both bagging and pasting allow training instances to be sampled several times across multiple predictors.
So my understanding here is that if you have the same predictor, so if I have a logistic regression model and I'm sort of trying to sample for training from, say, I've already done one round of pasting. Suppose if I want to sample another round, I cannot take the samples that I took in the first round.
No. So the way how it is done is, first of all, you need to create your samples and feed it to the models. So I'm not sure like the name of the person, but what he was saying is how it is done between both bagging and pasting.
So for example, a bootstrap sample means that you have to choose you have to choose n subsamples. You have to choose n samples, and let's say in other words, you have to choose a sample that's the same size as your original sample, right? So you choose n times with replacement, and at the end you have a sample that that has many repeated measurements. So only 63% of the sample will be unique. Now, if you're doing pasting, so 63%, to go over that point again, if you do a bootstrap sample, you'll only get 63% unique samples, or 63% unique samples, and the other 37% will not have been chosen. And those are called the out-of-bag samples. But if you do pasting with n, if you try to draw a bootstrap sample, sorry, it's not even the right term. If you try to draw a sample of n things with pasting, you only get one possibility, and that's the whole data set, right?
Yeah, also, are we slightly confusing training time and actually prediction time? Because at training time, they're all independently trained, aren't they, on the data? And each one could be either bagging or pasting, depending on whatever we chose. obviously at so at training time, there's no correlation between the data sets, is there? They're all independently being trained in parallel, having chosen bagging or pasting. Yeah.
Well, it seems that if you have pasting, this is one thing that I don't understand in the text. They're saying that when you do bagging, the samples are in some way less correlated, but I think that's the opposite. I think when you're doing bagging, now you have within each sample you have correlation, and then if you compare one sample to another one, you could also have correlation. So, whereas with pasting, if you compare one sample to the other, they're not correlated because they're all different data points.
But in bagging, it's also different data because you replace the duplicates after you sample.
No, no, it's that means there's duplicate data in every bagging sample. There's duplicate data, and from one bagging sample to the next, they could share a lot of examples in common. Whereas from one pasting sample to the next, they won't share any samples in common.
That's the way that I understand it as well. So I'm a little curious.
Isn't bagging what the central limit is saying? The central limit theorem, because that theorem says you have to randomly choose n samples from a population. It doesn't say that you're not allowed to replace them, and in that situation you have a certain level of variance. But if you're not allowed to replace them, then it doesn't apply as much. So I wonder if that's why the variance is lower in the bagging.
I don't understand. I mean, my understanding of the central limit theorem has nothing to do with replacement. It's just you're adding, the more and more samples you add, the better your central limit becomes, the better your estimate of the mean becomes.
Yeah, I thought it was any n from the whole population, that you couldn't kind of not remove some from consideration. But yeah, I'm a little bit of a novice in this area myself. So yeah, okay.
So here's the thing that I wanted to throw out to the group because I don't really understand it. This is on page 195, and this goes to the point that we're discussing. It's at the top of page 195, and if you have the Kindle version, it's right near or below figure 7.5. Yeah. Bootstrapping introduces a bit more diversity in the subsets that each predictor is trained on. Okay, that to me isn't true. And then it says, so bagging ends up with a slightly higher bias than pasting.
Yeah, that's counterintuitive to the way that I'm understanding.
Yeah, and then it says, but the extra diversity also means that the predictors end up being less correlated, so the ensembles of variance is reduced. This whole sentence doesn't make sense because bagging predictors are more correlated than pasting predictors because they have samples in common. And so it would seem to me that pasting would seem to me that pasting would give you less correlation rather than saying that bagging gives you less correlation.
Yeah, Joseph, you're right, and but the second part seems to be correct, right? That if you change the first part to be consistent with what you're saying, the second part of his statement then would be accurate. Is that not true? Meaning bootstrapping introduces less diversity, let's say, as per the argument you presented, in the subsets that each predictor is trained on. And so bagging ends up with a slightly higher bias than pasting.
Okay, so let's change. So if we change that word to in the sentence, bootstrapping introduces a bit less diversity, right? That's what you're saying.
Right.
Then the second part is true.
Right.
Let's see, higher bias. Yeah, that makes sense. And then let's look at the third part. But the extra diversity also means that the predictors end up being less correlated.
Okay.
So here we have to change it again. We have to say it's more diverse.
Yes. Yeah, because it is not, as per your argument, then it's not less, it's
it is more correlated and the variance is increased if we are flipping everything.
Yeah, and that's why I said that the variance part of it is not a guarantee either way. But that's why I do agree with what Joseph is saying. This thing just confuses the whole argument.
Okay, so the way how he has it, written, that there is more diversity in the bootstrapping, in the subsets. That's correct. Why is that?
No, it's not. It's not correct.
Okay.
Okay. Remember, bootstrapping is where you choose with with replacement, and that's why the bootstrap samples have less diversity than the pasting samples, which are distinct from one another.
Right. Okay. So
right,
let's take a second and think about it. So more diversity or less diversity. So when you have bootstrapping, meaning the subsets that you have, they have replacement on them. So they are like more different. They are more different than just really taking the data and just splitting it on, okay, this is one subset, this is second subset, they're all different. So this really introduces more diversity in the subsets themselves. Yeah, like the overall now, because the subsets, instead of being, for example, evenly like divided, okay, you have 1,000, okay, and you take 100 here, 100 here, and 100 here, and 100. Now what you instead of having it like that, now you actually have the hundreds, but those 100, the subset now is diverse because it has, some of them are replaced, so some of them are redundant. So in a way, and the end result is, again, the generalizing. You're actually trying to make it generalized to all this new. So I can see the confusion, but the way how he has written it, that it introduces more diversity, that is fine, because that's what happens actually on the different subsets.
So Salim,
sorry,
if I were
it just
to
means
sorry, go ahead.
I just wanna mention that it depends if the diversity we're saying is like I think what Salim was getting to, within the sample set that we have for each one of them, or within or between, right? Because it's true that if we allow the samples to be repeated, then each of the sets is going to be more unique, and then that's the one you have diversity. Whereas in the pasting, you cannot have that uniqueness of this particular subset had 10 repeats of that particular record, right? So that's the part that I believe that between the different subsets, that's when you have more diversity, because they tend to be more unique. They can have more repeats of one particular sample, which you will not see that on pasting.
So the diversity is really within each sample that has been taken, and less on between two samples that are drawn.
Yes, okay, very well. So
I think the probability of any individual sample being chosen is higher when you bag than when you paste, thereby, and that leads to what the earlier two people were saying and Salim was saying. It seems like that's the way to think about it, is the probability of any particular sample when you allow for resample to show up in the data set is higher than if you didn't allow resample, thereby causing more diversity in your set than if you didn't allow for resample.
Which in turn increases the bias, right? Because now there is, and that's exactly what he says. He says with a slightly higher bias than pasting, which is true.
Yeah. So, I mean, the way how I actually look at it, you need to compare, let's say I am training with 10 different decision trees and using bagging and pasting. So each of the output of the decision tree will be different, because my different decision tree would actually see a very different set of samples in bagging versus pasting. Let's say I wanted to go with like 70% of total training data set that I have that's available. Then in that case, bagging sort of creates a very decorrelated decision trees compared to pasting.
But for this data set, coming back to that question where we are discussing regarding whether the different data sets are uncorrelated or let's say exclusive or not. So in that case, just think it this way, like I will refer to the question that a point that someone put forward, that say for example we have got 100 samples, fine. Now we are coming up with a random forest which is having on, let's say, bagging classifier which is having 10 different classifier. So we would need 10 data sets for that. Now, if you want to come up with a 10 data set and you have got 100 sample, let's say, in that case, and if you want to create data set for each model that will have, let's say, 70 samples in it, then you can't have 70 distinct data set out of the 100 samples, right? So definitely the interdependency or inter overlapping of the data sets will happen.
In pasting more.
In pasting more, in yes, in pasting more, in bagging less. But the point is that in both of these things, that initially that we were discussing, that all the data sets are exclusive, they are distinct. That is not the case, right?
It will never be exclusive. It will never be distinct. It will not be 100%.
It will overlap. Definitely, it will overlap.
Guys, in the interest of time, let's sort of continue along and then sort of continue this conversation or discussion on Slack, if that's fine with everyone.
Yeah, let's do that. Yeah.
Okay, cool. So essentially, one of the advantages of doing bagging or pasting is that you can actually do everything in parallel. So every predictor can be trained in parallel on a different CPU core or different servers. So this makes it very fast and scale really well on large data sets. So that's an important consideration to keep in mind. So the next sort of thing is the out of bag evaluation section. So this was sort of discussed in the chat as well. So essentially, when we are doing bootstrapping, which is with replacement, every predictor is seeing about 63% of the training instances. The remaining 37 are unseen. And so what out of bag evaluation allows us to do is that during training, the instances that are never seen or the out of bag instances can be used as a separate validation set. And therefore,
Sridham, one question here. So these numbers came before as well, the 67% and 33%. How come these numbers are there? Like there is no A on that, clarification on that.
So
it's in the chat.
It's posted in the chat, in the Zoom chat. I think it was just posted by Joseph a little while the discussion was going on.
Okay, thanks. Yes.
So essentially, the 37% that are never seen, you can basically run cross-validation across all of those for every predictor. And then you can average those predictions, sort of the average sort of, you can evaluate the ensemble by averaging out the results of cross-validation on each of the out-of-bag instances. So that gives you a good measurement on how your model is likely to do on the test set. So in this code example, if you see, essentially what is being done is you have a bagging classifier. So this is effectively a random forest. So it's a decision tree classifier that's being bagged. There are 500 decision trees. We are sort of doing bagging, so with replacement. And additionally, there's this argument that says, give me the out of bag score for every estimator. And then when you run it, you find that the out of bag score is about 90%. So that's like saying that 90% is my average out of bag accuracy across all my predictors. And then when he runs the model, the trained model on the test set, you get this accuracy of 91%. So in a sense, it's giving you a measurement, provided your cross-validation has been done properly. It gives you a sense of how likely your model is to do on the test set, which is kind of a nifty and nice feature. So the next section.
I have a question. Sorry. So each predictor is evaluated on its own out of bag error, and then we average all the out of bag errors, right? Is that right?
Sorry.
So we suppose we have say 10 decision trees. Am I audible?
Yeah, I can hear you.
Okay. So we evaluate the out of bag error for each decision trees on its own, and then we average all the out of bag errors. Is that right?
Yes.
Yeah.
Correct. That is correct.
Okay, but we kind of assume like this whole thing should work even if each predictor is a poor learner, right?
Correct.
So what if all my accuracies are really poor? So my overall accuracy should actually be quite poor, and it wouldn't be a good estimate of my ensemble, right?
I mean, like there's
your ensemble is every estimator put together and then averaging the prediction. So why wouldn't it be a good representation of the
So my out of bag error is calculated using the ensemble or using my individual predictors, which was what I asked in the beginning. So out of
I
bag
think
error,
it's
is it?
individual predictors, whatever 37% is left out, you calculate your accuracy on that, and then you average that across your different ensemble, different trees.
Right.
So this is
So
the other problem that I agree with you, is that you can't use OOB as a substitute for like a validation.
exactly, yeah.
Because you're looking at different things at different times.
I mean,
And
what
and
the
each learner
comment,
could be, yeah, go on. Sorry.
No, I was just going to say what the comment is here is that it's a quick way to know how likely your model is to do on a test set, but it's not a substitute for cross validation. That's so what I meant to say is, like, if you just took this and since each individual predictor hasn't seen these instances, it's like getting cross validation for free in a sense. That's what I was trying to imply.
But it doesn't make sense to me, because our main premise is that each predictor is just slightly it's a weak learner. It's just slightly better than a random guessing. So if I just take out of bag of each, then I'm going to get really poor out of bag accuracy, right? Which wouldn't actually which wouldn't actually talk about how good my ensemble is.
It's not a weak learner, and because each predictor is a tree, right? Is a tree, and a tree is already an ensemble of weak learners. So the tree itself is a strong predictor.
I think that's an extreme case, Gautam, that you're pointing out, that's slightly above random. The tree is not going to do slightly above random. It will do
right. But
better,
yeah, I was
right?
just talking about the concept. Like, I mean, it could be the case that out of bag error is not at all indicative of how good my classifier is, right?
So it would be an indicator, but it would help you prevent the problem that you're talking about, because by doing the OOB, if you get poor results right there, you know that your individual classifier is bad. So just by ensembling, you're not going to get better. So I was thinking it would help you prevent the very problem that you were talking about by doing the OOB rather than having to run the full cross validation.
Exactly. So it's like a proxy. It gives you a quick insight into how your model is likely to do when you're ensembling versus actually sort of going through that compute heavy process where you create your folds and blah blah blah, right? So it's just a quick proxy to give you an indication. Is this going to work or not?
Yes, but let's not call it like something like maybe like you're absolutely right. It is a quick proxy, but it's bigger than that. Like the out of bag error, it's valuable to give you a good idea how it is, how your training is. But again, you're absolutely right. I mean, it's a point that you may say, oh, okay, this is fine. And then you're just going to go ahead and run, because again, this is here, we're doing all this and we still have our test set aside. That's the end goal. And then you can go and directly go to your test set. And sometimes you can be like, you know what, well, let me actually do my validation test, whatever it is, for example, the cross validation, and then go to the test set. But it is the out of bag error, it's a good practice to actually to look at it every time we're done training.
So in that case, if we have a out of bag error, poor out of bag error, like a huge out of bag error, then should we go ahead with that ensemble, or should we look forward to create another ensemble?
Should probably revisit your data and see what's going on, or think about why your performance is bad. So if something's wrong with your out of bag, it means that there's something else that's going on that you're not taking into account, and you should check. There's no point of going further without actually seeing at least a reasonable out of bag.
So Saram, would it be fair to say OOB score is always less than or equal to your validation?
I would. That's a tricky question.
Well, I mean, yeah. So here's the thing. Like, yeah. I mean, it's we don't need to compare them. This is better. I mean, if this is going to be higher or this is better. But as my fellow said, yes, the out of bag can give you maybe, oh, there is something wrong, and then here with the decision trees, it's easy to go and debug, right? Because we're going to get we can interpret this. So, for example, one way that he showed here that we can see the probability for each training. So for example, one way how to debug is to go see, oh, okay, there are instances that had 51% this class and 49. So those are instances that the algorithm was the most confused about. So maybe, so that's one way to debug. Why are those like 51, 49 instead of actually what we really want? We just want like in the 90s and the low 10s. And then we can
we
go.
have like 500 trees here, right?
Yeah.
So the looking at the tree, kind of the decision tree helps, but when you start entering this domain of random forest and kind of interpretation, again, you lose that, right?
Well, but you still have the interpretation on your random forest. Even if you do it, no matter how you do it, you can still get the feature importance. And I think we will get to it. So I think there is a feature importance section that I believe we'll get to. Yes, there is in a bit. So
okay. So so let's just continue to move on. I agree that a lot of this would probably benefit from sort of code examples and seeing how things work out. So for the next session where we're sort of completing the rest of this chapter, I'll sort of make sure that we have some code to play around with and discuss. So in terms of the next subset, the random patches and random subspaces is kind of easy to understand if you look at this picture right here. Essentially what random patches is that I'm going to take all of my training data, but I'm only going to sample a subset of the features, which is like if you look at this diagram, if you took this entire screenshot, right, this whole black and white screenshot to be the training set, you are going to sample across all the training instances for sure, but you're only sampling, say, a subset of the features. And that's what random patches is. Whereas, sorry, this is random subspace. I do apologize. I misspoke. Whereas with random patches, what you are doing is not only are you sampling a subset of the features. So in this case, you're sampling features 2 and 3, but you're only sampling a subset of the training data as well. So that is another way to sort of improve sort of your model's performance. Does that kind of explain things? So the way you can do that in code is just by choosing the bootstrap option to false for random patches. So that means that you are going to not select with replacement. So meaning that it's kind of like pasting, but then you are going to select your max samples to be 1. And wait, let me read this again. So keeping all training instances by setting bootstrap equal to false and max samples to 1, but sampling features. So that's what we're doing. So right here. And then we are going in the random subspaces method, we are going to set the max features to a number smaller than 1. So essentially this diagram really helped me understand what was going on in terms of random patches and random subspaces. Any questions here?
I guess yeah, go ahead.
Just one quick question. So in this technique, this is the part that I had a hard time understanding and following mathematically. And if somebody can offer a little insight here, if we are tracking which of these features are being used in this random subsetting, and ultimately we stop when all of the features have been used at least once, then how is this really applicable versus just keeping all features as one single model? How is this an improvement? Because we're just taking random patches, but aggregating ultimately to all features counted at least once. How is that an improvement over taking it all in just one single go?
So you can, the way that I sort of reconciled it was that you can think that each model is only focusing on a subset of features and it's making its predictions solely on those features. And that introduces some kind of decorrelation, if you want to think about it that way. I wouldn't say decorrelation, that's too strong a word, but essentially, like if every model is only taking, so let's say that I have one model that's only looking at this square right here, right? And I have another model that's looking at, say, some features here and then some features here. It's ignoring 2 and 3. the predictions, depending on the feature importance, could be wildly different. And therefore, you are sort of introducing some diversity. In that sense, it might be better. Does that kind of explain it?
I mean, the other issue, I guess, is going to be if you take all the data, it might overfit.
Mm-hmm.
But one of the reasons you would take subsets is, I guess, to avoid that.
Yeah,
that's the key. That's the key. It regularizes. To take patches is a regularizing device.
Yeah, this is why I asked if we had code this. I hear you all, and I'm reconciling it in that same way, but it seems a little theoretical to me. Sort of I have to have faith that that's indeed what's happening. I'd love to be able to actually work it out and see it.
Yeah, it'd be very easy to do that just by setting the switch, by running the model, same model, and setting the switches differently to choose random patches or not, or So yeah, that's easy to check out. Maybe we can do that next time.
Yeah.
But again, the real question can be extended, right? Because the point being that it's, even if you code it and you apply it, you'll have to gain the appreciation that it does it based on its application to a ton of data sets. Because at the end of the day, if you code and run a sample, that doesn't mean you approved it, because it just means that for that data set, it worked. So when the book says it, then you have to take it on faith that it's been applied for a large variety of data sets, and that's held true. Because otherwise it's a single code example, and I would still choose not to believe, and I would choose to believe that we just got lucky.
I think it's also choosing a random subset of features at each split. So in the end, you might have all the features selected through all the splits within one tree. It's just when you actually do try to select the best features to split on that node, you're only trying to select a subset of features. So that actually helps model in some ways, if that explains.
Yeah, that's the one question that I had. The way he discusses random patches, it's not clear as to whether it's happening as you said, Wencheng, that is, this is the way it happens in random forest. When you choose a random subset of the features and you only allow those features to be used for splitting, that's the way the random forest handles that random features aspect. But it seems the way he talks about it, that random patches says that for each tree, you only get to use a subset of features. For all the splits, the same subset of features gets used for all the splits. In other words, each tree is really being built from a subset of the data, from a patch of the data. I think that's the way it works in random patches, and that's a little different than the way it works in random forest.
I think when
like
Chang is right. Yeah, sorry, go on.
I was just going to say it's like increasing the randomness as you go on from patches to subspaces to random forest.
Yeah, there is this thing he talks about, like bootstrap for features. So that would make sense only if the sampling is done at the split level. If the sampling of the features is done at the tree level, then bootstrap for features doesn't make sense, right? Because if you just take the same feature twice for a tree, it doesn't make sense. It's like having the same feature. But if you're doing this sampling of the features at split level, only then bootstrap for features makes sense. So suppose you use a feature at a top split, you can use the same feature at a lower level split.
Yeah, but what I'm saying is instead of allowing you to randomly choose 4 features at every split, which is what you would be doing in random forest if you said let's choose 4 of the features and each time 4 random features for each time we have to do a split. That would be the way you do it in random forest. But here, and so those 4 features could be chosen from the full feature set, 4 features at random each time you do a split, and that way you will eventually see all the features. But here it looks like for random patches, you only get to choose a subset of 4 of the features to build this tree, to build the tree out of this patch, and then for the next patch you get to choose a different subset of 4 features, and so on.
Yeah, I agree with you, Joseph. It's subsetting the features right at the beginning and then randomizing the choice between them. The way I thought about it, and in fact, the way it seems to explain it is, think of the patches as going in the feature direction the same way that you would go in, the bagging or whatever the other term was in the number of samples direction.
Yeah, one is rows and one is columns.
Yes.
But how would the bootstrap value make sense then if you're sampling at the tree level? Like, doesn't make sense, right?
Why
If you're
wouldn't it make
bootstrapping,
sense? So
because bootstrapping means you are sampling with the replacement.
Correct.
Then what is the replacement aspect in when you're sampling at the tree level? Like if I'm sampling this feature A, then B, and then A comes again, that doesn't make sense, right? Because
Right, and so that's why Bootstrap, you have to have false. You have to have it false because you're not choosing a Bootstrap sample of the features. You're choosing.
This is like pasting.
Yeah, for the features, you have to choose a pasting sample because it wouldn't make sense to have two features being identical. Two of the features in your subset being identical.
Exactly. Quick question for the group. So since we are kind of over time, would it be fair if we sort of continued our discussion in the second session? The plan would then be sort of to finish reading the rest of this chapter and then sort of include our discussion of random forests and extra trees into that. I'll also sort of work towards getting maybe some code so that way we can sort of go through maybe for about 30 minutes on some of the things that we discussed, especially like the bagging, pasting, and sort of some people had questions on how it reduces variance. So maybe I'll try to see if the companion notebook for this has some examples that we can leverage. Would that be reasonable, or would you guys prefer to complete this discussion and then leave the rest for next session?